Hey, can I ask the question while we are waiting for people?
Yes, yes, please.
Uh, yeah, that's just to like be on the right side about electron spins.
Mm-hmm.
So, am I understanding it correctly that they can basically change their spins at will when they are like jumping on orbitals? Or is it more complicated?
Mm, well, depends what do you mean. Um, when they are on some orbitals, basically, if there is an unpaired electron, and we do not know anything about the atom, we actually do not know anything about that spins. So to let's say prescribe them direction up or direction down, we need to put that atom into some sort of magnetic field. So then you will have that magnetic field, and then we can say that these spins can be up or down. If you
Mm-hmm.
are just
But
drawing a picture, it doesn't really matter. So do you draw them up or do you draw them down? Um, but if we are talking about some sort of physical situation, so um, we will probably have some sort of device and some sort of magnetic field, and this field will define the orientation for spins. Is that
mm-hmm.
what you were asking, or maybe?
uh, well, yeah, but like when we uh, when an atom hybridizes its orbitals,
Yes.
we can have like we had two electrons on one orbital, but now they're on different orbitals. Uh, do their spins like change in this process when they bind to another atom, for example?
Uh-huh. Um, yeah, that may be. The simplest example I showed you was with two hydrogen atoms. So we had one hydrogen atom, so and it has one electron, and suppose it has some spin up. So I have some coordinate system, so on and so forth. So if it will create a molecule with another hydrogen atom, this electron should have spin down. If they
Mm-hmm.
both
So
have
it won't
spin
react
ups,
with spin up.
yeah, so it will not pair up with spin up. That's because when we have two hydrogen
Mm-hmm.
atoms together, they create now molecular orbitals. And you know, the Pauli exclusion principle says that you cannot have two fermions in one quantum state. And since they will be living on one and the same orbital, so they have basically all their quantum numbers the same, except spin quantum number. So this last quantum number is our last resort to somehow make difference between them. So fermions do not like being in one and the same quantum state, and since spin is one of the quantum numbers describing this quantum state, in case they live on one orbital and all the rest quantum numbers like energy, momentum, so on and so forth are the same, so the last resort is making them spin up and spin down. So this is the only way to connect two
Okay,
hydrogens.
thank
Yeah.
you. Mm-hmm.
Otherwise, we will just have no bond between them. Well, everything, of course, goes a bit deeper and deeper. So I told you that the rabbit hole is quite deep, and actually, if you take Schrödinger equation and calculate all the things, you will see that there is part in the Hamiltonian that describes energy of the interaction, and there is part that takes spins into account, and there is, I guess, more evident on that mathematical level that you have some addition, something added to the energy that depends on that spins, and in case they are different, you have some additional binding energies, something that helps to keep these atoms together. Well, we'll be having some talk about spins, I guess, today, uh, because today's lecture. Okay, how did I make this full screen? Aha. Okay. Still. Yes, I see a question. Please.
Yeah, I have a question about the home task that we had for today about the second task. I wrote as you asked, and also I put the like SP3, SP2,
Mm-hmm.
like to each, I don't know, to each component that we have. Is it was necessary or not? Because I didn't understand that, so I put them for the case if I needed.
Um,
It
I
was the second task in today's
I
lecture.
guess it was about carbon atoms, yeah, and okay, mm, okay, like let me find it somewhere. Well, I'm basically. Oh, it freezes. So lecture one. No, not this. I'm not sure if I can open this because everything freezes incredibly. Okay, so this was the problem. uh, well, what I just wanted is somehow designate what is the hybridization of each of these carbon atoms. So, however you do that, it doesn't really matter. It should be just understandable that you treat this carbon atom as sp something hybridized, and this carbon atom as sp something else hybridized, and so on.
So can
So,
you it's like something is look just a second. Um
so unless
okay.
that's understandable, that's pretty okay.
So it's something like that, is it okay?
um, I wish I could see. Yeah, I
I don't see
guess.
if you
I guess. Yeah, it seems like they are designated, and I see which atoms are which. So it's not a
yeah,
problem. Yeah, I
yeah,
don't think you
okay.
should worry about it. So if that happens, that I wouldn't be able to decipher that, I guess we can communicate through messenger, or I would just request for you to resubmit or whatever. So I don't think that's a big problem anyway.
Okay, thank you.
Yeah, so should not worry about such minor things. So okay, now let's get to our today's lecture. I guess I have a lot of material to cover, but I hope this lecture will be well interesting for you, as there are certain parts that are rarely included into classical chemistry courses. I mean, school level courses. This is more like a real university level course. So the problem in question is structure of chemicals. So I already told you that depending on the structure of chemicals and all that sort of orbitals and so on, we may or we may not have certain chemical reactions and so on. So today I want to talk to you how do we get some idea about how all these chemicals really look like, because of course we cannot see atoms with naked eye, so we need something, some machinery, and I will show you that machinery. That's first of all. The second thing I want to show you is well, what to look for in the structure. So not all features are, let's say, equivalent. So something is more interesting, something is less interesting, and I want to show you what exactly to look for when we are talking about structures. Okay, so I already gave you this link. So here is some sort of program that, let's say, estimates the 3D structure of the molecule that we draw. It's a really crude estimate because to get something better you need to perform quantum mechanical computations, and there are certain libraries that are able to perform that, but you really well, you really need to spend some time to get a grasp how to do that and to install all that thing and maybe know some Python or whatever to use them. So maybe someone heard about software like Orca or maybe something different, but you should know there are even open source software that is capable of calculating all that 3D structures and electron electron density and so on. Okay, here is probably some standard view of of some different structures, and what I want to show you, these pictures are probably closest to that pictures that you have drawn at school. So you see that there is some sort of hydrocarbon framework, because it's organic chemistry. It's basically chemistry of different, let's say, chemistry of carbon. It can be in form of chain, in form of a ring, and it may support some sort of functional groups. Hopefully you know what it is. So here you see a branched chain, you see a ring, and just simple chain, and so on. In the chemicals, the functional groups determine the way the molecule works both chemically and biologically. So that carbon framework, well, it has, of course, it has to do with the properties of the chemical, but probably the most interesting for us will be different functional groups. So here you see the amino group. Here it is. Yeah, you see carboxylic group. So this is some amino acid called alanine. Probably we will meet it later when we get more into the biochemical part. So here is lysine. It has an additional amino group. So we see amino group here and amino group here. And methionine, one more amino acid that you can find in nature. Okay. So what's of that? The way how we draw chemicals is pretty different from the way how do they look like in 3D. So probably it's not a surprise for you because we draw them on something on a plane, and all the chemicals they live in 3D. So our drawings are, let's say, a little bit far from reality. The problem is that even in this planar view, we can draw them using different methods. And some of these methods are better than the others. Why? Because they are a little bit closer to what we have in 3D. So here is linoleic acid. Here you see the same chemical drawn in different ways. So one way is drawing all the possible atoms that we have and all carbons and so on and so forth. And here you see they have this interesting form. Here is another way writing that using some sort of shorthands like CH3, CH2, so on and so forth. Here is some sort of school method of drawing this sort of chemicals. And the last one is basically the method that chemists will prefer. So you see we have no redundant hydrogen atoms here, so we imply that whenever we have carbon atom, we even don't draw carbon atoms. So we just imply that we have carbon atom at each of these nodes, let's say. So carbon atom here, 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 and so on. And we always imply that carbon atom has 4 bonds, so we can calculate how many hydrogens are missing. So here we have a carbon atom. You can calculate that we are missing 2 hydrogens. So hydrogen 1, hydrogen 2, and so on. So we are basically seeing a carbon skeleton. And hydrogens, they are just hidden from us. Depending on the situation, we may somehow outline our functional groups. That may depend on the problem that we are considering, because we may want to emphasize something. And we will do that all the time. So here it's once again linoleic acid. And here you see all the shorthand notations that were used when creating this view. So you see that everything in the chain represents a carbon atom. So you see that all hydrogens are implied, so we calculate how much hydrogens do we need more. So here, for example, all 4 bonds are used, so we have no additional hydrogens. And here we have only 2 bonds used, so 2 more hydrogens implied. And here is a reminder for you that if you are drawing organic structures, they should be realistic, economical, and clear. So the main idea is clearness, so everyone should understand what exactly is the chemical that you want to represent. Why do we draw this with all these sort of kinks? Here is here's an example. Let me delete everything and let's draw I don't know, something like this. So I'm drawing really bad, so never mind that, but please look at the 3D structure. So what do you see? You see the same sort of kinks we used when drawing the linoleic acid. Why is that so? Who remembers from the previous lecture?
They're trying to be as far away from each other as possible?
Yes, absolutely correct. So these orbitals well, all these orbitals, they are trying to be as far as possible. And it turns out that the furthest they can get, it's when they have so-called tetrahedral angles. So these angles between them, you can draw in some sense a pyramid. Oops. Once again, I'm drawing black on black, which is no good. So we can draw a pyramid with that carbon in center, and you see that all these other atoms, they are basically at these ends of the pyramid. So that's what we have. And of course, this is because all these they are, let's say, sp3 hybridized, and you see that it's some sort of pyramidal structure. Now what happens if I add a double bond? So I add a double bond. So that drawing is bad, but 3D should be more or less okay. So what do you see? Here we have sigma bond and pi bond. And what it makes with the structure,
They became more like a lane
They are
rather
planar.
than pyramids.
Yeah, so they are planar, so you can see that I can draw a plane, and they all are planar. Why? Because we have pi bond here, so there is a large electron density above and below. So all these other bonds, they are trying to get away from that high density, and so they are, let's say, living in the plane of this double bond. So that's what we have. Okay. um, oh, their question. Yes, optimal position. Yeah, some sort of problem of finding some optimum. Okay, so that is the reason why we draw all this like this way. So with all these kinks, and that is the reason why when we have these double bonds, we may have let's say these bonds coming on the one side or on different sides. We will talk about that. It's called cis and trans isomery. Okay, a little bit one more piece of notation. Here is some chemical, well drawn with all bonds represented as sticks. In some cases, you want to add some three-dimensional nuance. So you want to show how this hydrogen and this amino group are situated in the 3D space. In this case, you may use this sort of notation. So this bond means that this NH2 comes out of plane towards us. So if I have a plane of paper, so here is the plane. So all these atoms are living in that plane. So they are all in the plane of paper. So this group is coming towards us, so from the screen. While this dashed bond means that this hydrogen is beyond the screen. So this adds some three-dimensional nuance to what we draw. I've tried to reproduce that in our program. Okay, let me add one more bond. Let's say this is an H2. Let it add. Okay, CH3. Okay. So now I can add some nuances like making this bond here, this here, and calculating 3D. Okay, indefinite key. Well, guess I messed up something. Okay, let's redraw. Yes, I see a question. Yes, please.
Can you show where is like chiral bonds we have on this 3D and 2D? Because we'll have this in the home task. I saw that,
Yes.
so just join this one that about chiral
Well,
bonds.
it's all about chiral atoms, and chiral atom in your homework and basically here will be a carbon atom that has 4 different substituents. So if you have a carbon atom, let's say this one, so this one, so it has 4 bonds to how many different substituents? So one is methyl, so this is 1. The other is NH2, so 1 more. 1 is hydrogen, third. And fourth is this sort of carbon skeleton, 4. So it has 4 different substituents, so that will be basically chiral carbon atom. If I take different carbon atom, let's say this one, so how many different substituents does it have?
4.
No,
Because we
different
have,
different substituents.
like
So
we
three
have one
hydrogen
from
atoms
carbon,
and
another, and
the
3
rest.
from,
Yeah, and 3 from hydrogens.
yeah.
So you have 2 different substituents. Because we need the number of different substituents. So not just...
Okay, yeah.
So
Got that.
it should not just have 4 bonds, it should have 4 bonds to 4 some different things. And here it has bonds only to 2 different things. So one is hydrogen, one is, well, all the rest of the molecule. So this one will not be chiral. While this one will be. Okay. So we're going a bit ahead. Good. I see some more comment. Yes, somebody says 2, and that's absolutely correct. Good. Here are some sort of shorthands often used by chemists. Well, you shouldn't remember that by heart, just know that there are such things. One of the previous lectures someone asked me what is this ME, so here you see that's a methyl group, and maybe you will see this ET, ethyl group, and maybe pH, like phenyl group. Okay. Here are 2 useful links for you. One is to ChemSpider and the other is to MolView. These are sites that help you searching chemicals if you know their structure. So you may not know, well, how to correctly name them or something like that. So you may want to use any of these sites just to go there and search for some chemical. That may be useful if we ever do some problems that involve some sort of research on certain chemical and so on. So you can just go to this site, you can choose structure. Here you can draw this structure, so it's a little bit crowded here and was for some time. Okay, so let's just draw something trivial like benzene, and I want exact match, and I ask for search. And here I have information, so it's really benzene, some molecular formula, mass, so on and so forth. So you may get some sort of properties, some spectral data, and so on and so forth. So interesting information you may find here on the chemicals that you don't know what they are. So that may be useful. Good. Okay, what else? About the structures. So I told you that we are trying to draw molecules to more or less resemble the 3D structure that they have. But I should remind you that single bonds can rotate. And you see that this chemical, if you calculate that with all that quantum things and so on and so forth, the minimal energy is acquired when we have this sort of conformation. But in practice, you always have some non-zero temperature, and molecules are moving, colliding, and so on. So we may probably expect that some of these bonds will be rotating. And here you see an example how all these bonds rotate and what they make with the molecule. Maybe we'll get to that a little bit later when we talk about proteins and protein folding. But anyway, you should know about this effect, and that we do not represent that in our drawings, but in some cases, if you measure something, it may somehow manifest. Good. What else? So rotation or bond breaking. So structures that can be interconverted simply by rotating about single bonds are called conformations of the same molecule. So conformations of protein, conformations of some molecule. If structures can be interconverted just by breaking and probably restoring some bonds, we have different configurations, and they are called stereoisomers. So here's an example for you. So these are conformations. So you see here, if you rotate around this bond, you get from here to here. So it's just rotation. Now this thing. If you rotate around this bond, you can get from here to here. So hopefully you see that. So when I rotate like so, this group gets in place of hydrogen. Hydrogen goes back. So now he's in the plane of the screen. Then he goes back beyond the screen in place of the methyl group. Methyl group goes forward and now is coming off the screen. So here we have it. And here is another conformation, much more tricky, with a ring. I guess I have some video example for you later, so I'll show it to you a bit later. And these are configurations. So you cannot get from here to here just by rotating single bonds. If you think for a while, for example, if you try rotating around this bond, you will see that you cannot get this structure. That's impossible. Here is another interesting thing. Rotating around this bond will not get you from here to here. You cannot. Even if I try. So what happens? Well, the lower part is exactly the same, so let's try rotating the upper part. So here I see that the acidic group is somewhere behind the screen. Yes, I see a question. Yes, please.
Yes, sorry for interruptions. I would like to ask about the home task, because the first home task, some of our students don't have a possibility to put it, so they don't have the like the button to access
Oh,
at the home task.
there is no button.
Yeah,
I
module.
guess I need to contact.
It's me.
Yes, please.
Yes, it's me. I don't have this button.
Uh-huh. Okay.
Maybe it's too late, but I tried like in the afternoon.
Mm, um. Okay.
So basically, we had a situation. It's like another like subject, so
Mhm.
it's kind of trouble of Moodle,
Mhm.
and sometimes like the teacher can fix it, or sometimes the teacher just need to wrote some tech support just to ask them to add this button. So it's
Uh-huh.
basically just a mood thing that is not about you, just for you know that some of our students have the possibility to add this button.
Okay. I'll write to support, or I'll ask someone from our office. What do we do in this case?
Yeah, thank you.
Maybe
Sorry
someone
for
can fix
interrupting
that.
you.
Yeah, it's good that you said, because I had no idea what's happening there on technical level. So I'll ask them what to do. Well, if nobody can do anything, you will just send me a PDF file, and I will try to somehow
Yeah, just mention because we
break
have the
it by
deadline
hands.
up to tomorrow. So we just
Mm-hmm.
mentioned because like tomorrow is like the last day for the home test. That's why I'm asking about
Oh,
it.
okay. If there are such problems, I'll extend that deadline. That won't be so that won't be a problem. I guess I'll ask someone what to do in this case, and if they can fix it, they'll fix it. If no, I think we'll find some workaround.
Could you please return to the example with the conformations and configurations for a sec?
Yes, yes, please.
Thank you. Yeah, so regarding the conformations, is that second molecule rotated around the single bond, or the double bond changes the place somehow?
The second molecule, you mean this one? Or this one?
Yes. Yeah, that
one.
one you showed. Yeah.
No, that's rotation around exactly this bond. So if I am rotating this thing like so, you see that this double bond starts going this way, and this thing remains parallel. So I can draw how it was here, and you see how similar they are. So that's rotation around this bond. So it's really a conformation. While in this case, we will really need to break a bond and then somehow recreate it. Okay. So here is here is one more slide. We have ethane conformations, and here is the example of rotation, basically around one single bond, and you see that we may have any angles that we want when we are rotating around this bond, but they all have, let's say, different energies. So if we draw a plot of energy versus our rotation, you see something like this. Looks like a sine curve or something like that. So one conformation is called staggered. It's this lower one, and one is called eclipsed. And you probably might guess that in the eclipsed conformation you have these bonds interacting, and they don't really like to be close. So they are trying to get to the staggered conformation when they are as far apart as possible. Well, because you have charges, you have negative charges, there are electrons, so on, and they are repelling just by the Coulomb's law. So nothing special here, but this is a classical example what happens when you have a bond that rotates. So here is another example of rotation. Here you have different orbitals that repel, and you see that repelling between carbon atoms and between hydrogen atoms, they are a little bit different, so these bonds have different angles. Okay, so and this thing up here is called Newman projection. So maybe we'll see that a little bit later, once again. So this is Newman projection. This shows us that we are looking along this bond. So this bond is here, and let me choose another color. These hydrogens are these three hydrogens. So we see these three bonds. Then they schematically draw some sort of circle just to make difference between hydrogens that are in front of us and hydrogens that are on the far back. So here are let me choose another color. Hydrogens on the far back, and here they are on the diagram. So these three. So nothing really special, just a convenient way to designate hydrogens and their position in the case of rotation around single bond. Here is one more thing. I'm not sure why cannot I make this full screen. Okay, let's let's make it so, because I don't see the numbers. So here you see energies that we need to rotate around a single bond. For butane it's just 12 kilojoule per mole. For something more complicated it can be a little bit more, 30 kilojoule per mole. But probably you might guess that we have some sort of conjugation here, so you see two double bonds. So it's not so strange that there is some higher energy for this sort of rotation. Here we have once again rotation around single bond, but it needs even more energy, 85 kilojoule per mole. And who can guess why? Why do we need in this case much more energy than in this case?
Maybe because an atom is more electronegative than C. Nitrogen.
It's not electronegativity, but it really has to do with nitrogen.
It's about bonds.
What do you know about nitrogen?
What
Is it
exactly
bigger and
would like
heavier?
to ask?
What about non-bonding electrons?
So nitrogen has 4 or 8, I don't remember correctly.
It has 7 and it requires 1 to be shared.
So it has
The 8th one.
let me draw that that color once again. So it has 2 non-bonding electrons, so a non-bonding electron pair. Here we have a double bond between carbon and oxygen. That's a sigma bond and a pi bond. Yeah, so a pi bond here. And here we have a non-bonding electron pair. So what will it do? It will interact with this pi bond. So in 3D we will have this electron pair interacting with the pi bond here. So it goes in 3D like this, and here we have that pi bond, here and below the same thing, and they are interacting. We will see that behavior in different reactions, so you may want to notice that nitrogen has that lone electron pair, and that electron pair may influence well, different properties that we observe. Okay, one more example, butane. So here is butane. Here I have even a model for you that may make everything more simple. Okay, so here is butane. So you see how that looks like in 3D. And now we want to consider rotation around this bond. So what do we need to do? So we look along this bond like this, and we will draw that sort of diagram. So here is the bond we are interested in, and we will draw the bonds that are in front. One goes to the methyl group, to go to hydrogens. Then a circle, and bonds that are beyond the plane. To go to hydrogen, one goes to methyl group. And here's how it looks like. So once again, we can rotate by any angle, but we have different energies. So this is basically the question of conformation and conformers. So butane can exist in an infinite number of conformations, so you can choose any angle. But there are only 3 conformers that realize some sort of potential energy minima. 2 are so-called synclinal gauche conformations and the anti-periplanar conformation. So you might probably guess that if we have 2 methyl groups, they are quite large, they are repelling each other, and they would like to be on the opposite sides of the molecule, or let's say as far as possible. So that shouldn't be a surprise for you that exactly this conformation has the lowest energy. Of course, we have 2 more conformations, this one and this one, called synclinal or gauche, where we have some sort of local minima of energy, and once again they are possible. Here you see so-called barriers. So to get from here to here, you should go through some sort of intermediate state that is not so energetically favorable. We will see that, I guess, in some next lectures when we will talk about reactions, how do they proceed, and so on and so forth. And probably there will be some sort of intermediate states and intermediate compounds that we are interested in. Okay. And here I have for you interesting thing, and I even have a 3D model, which is great. So this is the chemical. It is called cyclohexane. And here you see how it looks like in 3D. So this is not a flat ring like the benzene ring. So you see it doesn't have any double bonds, it is not aromatic or something like that, so not even close. And it's not planar. And here you see this chemical. And the thing is that this chemical can exist in a few different conformations. So I will show you, I guess, a small video about changing these conformations, just to show you that rotation around a single bond may be not so trivial like we might think. So let's check. The thing to notice here, let me start the video once again. Probably I'll pause it. Oh, that's great. Here you see hydrogens. They are drawn with different colors, with blue and red colors. Blue hydrogens are called axial. So you see that bonds to these hydrogens, they are sort of vertical. So they are perfectly vertical. These are axial hydrogens. Hydrogens designated with red are called equatorial. So they are in equatorial position. I know it may be a little bit too complicated to trace whatever here happens. Oh yes, I see a question. Yes, please.
So equatorial, that means that they completely fulfill, or what exactly?
You see that axial hydrogens, they are, let's say, they are vertical. So you have this sort of strange construction, and some hydrogens have bonds that are just standing vertical. So these are axial. Whatever is not axial is equatorial. So it tries to be in a plane of ring. Of course, I cannot say plane because it's not planar, but I guess you might guess what I mean.
Oh. So it's just about the position of atoms.
Yes, it's all about the position of these atoms. So what I want to show you, rotation around single bonds makes axial hydrogens to equatorial. So we started with blue hydrogens axial. Now something is happening, and now we finish with red hydrogens axial, and blue hydrogens are now equatorial. Well, it's maybe no big difference while these are hydrogens, but if you substitute them for some sort of functional groups, that will make a difference. So some chemical reactions will go only if the group is in axial or in equatorial position. So it may end up just locked in one of the positions because you cannot effectively overlap your atomic orbitals when performing this reaction, and if it is in a wrong position. If the group is bulky, it may want to be in equatorial position to avoid interaction with other axial hydrogens, because it has some large charge and it wants to be some far away from everything else. Yes, I see a question. Yes, please.
So basically, we rotate the atoms, or we rotate the I don't know, some elements, just to convince the results of what exactly we want to have, or what exactly we want to just to change.
It's not like what we want to change, but in practice, if we have some non-zero temperature, all these conformations will be present in a mixture. So you have some sort of chemical, but all possible conformations, so all shown here, they will be present. Well, so some more. So if you calculate the percentage, so some will be almost 100%, some different will be different.
We just mentioned about that some, I don't know, methanol or ethanol, if we will put them instead of
Hydrogen.
hydrogen, yet will be more likely that it's gonna be changed or exactly the same.
Yes,
So that's why I'm asking about it.
it will
So
be
we
much.
rotate it.
It will be
Yeah, we
much more
rotate.
likely to live in. I'll try to search. Here is, I guess, an example. So here I have some group designated by X. So here is some X group. It may, if we change conformations, you saw that it may be in axial position or it may be in equatorial position. So these are just two different conformations. So nothing more. But depending on what kind of group is this, it will interact with hydrogens in axial conformation and probably would not really like to be there, just because it is repelled by their electrons. And here is a table that tells us how strong is that repelling force, let's say so. So here I have conformation 1, here I have conformation 2. They exist in the solution or anywhere at the same time, but in a different proportion. I can calculate this proportion, so like the concentration of the equatorial conformer divided by the concentration of the axial conformer. So the higher the value K, the more this chemical likes to be in the when that substituent X is in the equatorial position. And what are the values for this K? Here are a few of them. So if this X is just a hydrogen atom, we have 1. So there is no preference between the axial and equatorial position. If I take methane, you see number 19. So out of 20 molecules, 19 will be in the equatorial position and 1 in the axial. Ethane, a little bit bigger group, a little bit bigger K. Isopropane, bigger group. So you see that percent with the substituent equatorial, out of all molecules now reaches 98%. Third butyl group, very large group. So you see the K is more than 3000 and probably everything exists in the equatorial state. So that's exactly what I mean by the fact that if we change hydrogens to something else, that something else may prefer equatorial position. So if it's something negatively charged, if it's something bulky, like third butane or something like that, we will probably have a very, very large disproportion in favor of the equatorial position. In case if we have some smaller groups, well, it may be not so favored by equatorial position. And that, well, we may see some effects of that if we consider certain reactions that go when, let's say, substituent is only in the axial position, or if it's only in the equatorial position. So that depends. So some reactions that may potentially go will not go just because you don't have this axial positioned conformer. So that's exactly what I mean. I see I have some link here, but I can't read. Why did I put it there? Okay, let's check what it is. This is, I guess, I have changed atom to bromine, but I'm not sure that it calculated correctly. I don't think so. It doesn't look right. Okay. I don't have bromine here in table, so what else? Before we go to isomers, I'll show you one more nice video of changing conformation of the cyclohexane, and we will move further. So once again, you see axial and equatorial hydrogens, and here you see how to rotate these bonds to get from one conformation to another. Good. Okay, now it's time to talk about isomers. So isomers are molecules of the same kind and number of atoms joined up in different ways. So here are some examples. Stereoisomers and constitutional isomers. You may have isomers that contain the same atoms bonded together in different ways. The connectivity of atoms in the two isomers is different than they are constitutional isomers. If the connectivity of the atoms in constitutional in the two isomers is the same, they are stereoisomers. And we will have enantiomers that are stereomers, and so are the E and the double bonds. So I think I will show you a little bit better table. Let's say here, because there are many different isomers. So here are some examples I want you to see. So we have isomers, we have constitutional isomers. So we have the same number and kind of atoms. So the methyl propane and butane have the same number of carbon atoms and hydrogen atoms, but you see they are differently connected. We may have stereoisomers. If you make a list of atoms and you write at each atom that it is to what is it connected, for example, carbon atom is connected to hydrogen and to some group and so on and so forth. They will look the same, but in 3D they look differently. Why? There are so-called enantiomers these are mirror image molecules, and here you see an example of R lactic acid and S lactic acid. So if we draw a mirror, these are basically mirror images of each other. The thing is that rotating this atom, so whatever I rotate it, whatever I do, I cannot make it the same with this atom, because it has a so-called chiral center. So this carbon atom is chiral. It has 4 different substituents. And that leads to the fact that a mirror image cannot be rotated and translated to transform into another, into the original chemical. So you may see that if you try, for example, transform this molecule into this one. So we have CO2H in the same position. That's okay. Let's try rotating here. So if I rotate this molecule a little bit, what can I do? I can place, let's say, what should when I'm starting rotate this OH goes beyond the screen. So it goes beyond the screen. This H for some time is still living in before the screen, in front of screen, and this goes into the plane of screen. But it doesn't look right, yeah, because we will have this hydrogen coinciding with this hydrogen, but these two groups will be swapped. So we will have OH in place of CH3, and we will have CH3 in place of OH. And if I try to rotate them even more, I will get something different. So two groups will be always swapped. You cannot get from here to here without breaking any bond. And that may be interesting in some cases. I will show you some problems later that these exactly effect influences. And we have diastereomers. These are non-mirror images. They can be configurational stereomers, or they can be cis-trans diastereomers. So you have probably seen some sort of cis-trans diastereomers when we have double bond. So here is an example. When we have a double bond, and this is trans to butene and cis to butene. So trans-butene has the CH3 groups on different sides of the double bond. This one has CH3 groups on one side. Well, cis-trans terminology is used to both double bonds and in cases you have some sort of ring structure. So once again, we have this sort of trans 1,3 dimethyl. I guess what that cyclopentane, probably. I don't see what's written down there. Yes, cyclopentane. And once again, you might see that we have a part that is above the ring and part that is below the ring. So here CH3 groups are on different sides of the ring, they are trans, and these are on one side, so they are cis. The thing is that this terminology, well, it can be used when you have two substituents on two different carbon atoms, but it doesn't work if you have more substituents. And for this case, we have so-called E and Z terminology. They come from German words entgegen, which means opposite sides, and zusammen, which means same side. Well, it's just some sort of terminology. I don't expect you to know that, but probably I need to show you that it exists. Well, that's actually a standard problem with all the terminologies, like in this case, we are just creating some sort of pretty arbitrary rules that allow us to describe a 3D structure in form of some sort of words. And you might guess that since these rules are pretty arbitrary, knowing them, well, it doesn't really make you better or worse at chemistry, but if you will read some sort of books, you will see this sort of terminology, and I want you to be to be not afraid of that. It's just some sort of way of describing how some substituents are positioned in the 3D space. So the idea is that you prescribe some sort of priorities to each of these substituents. Then you sort them in some order, so you see some higher and lower priority substituents, and then you see what happens to the higher priority substituents. So, like we had when we had hydrogen atoms and substituents, we were talking about cis and trans, looking by on the substituents. Are they on one side or on different sides of the double bond? The same case here, but we talk about higher and lower priority substituents. So first of all, we compare the atomic number Z of the atoms directly attached to the stereocenter. The group having the atom of higher atomic number D receives higher priority. If there is a tie, so they have the same atoms attached, then we make a list of atoms at distance 2. For multiple bonds, list each atom more than once. Each list is arranged in order of decreasing atomic number D. Lists are compared atom by atom, and the earliest difference tells you which group has higher priority. If there is still a tie, each atom in each of the two lists is replaced with a sublist of the other atoms bonded to it, and rule 2 is repeated. So it's just some sort of mechanistic rule that you apply and you get the number. So here is some sort of example. So here you see this carbon atom has lower priority than this one, because this is connected to hydrogens only, and this one has connection to another carbon atom. Once again, lower and higher priority, because this is connected to hydrogen, this is connected to carbon atom. Here is maybe a bit more complex example. When we consider one connection, we see that we have a tie, because one is connected to carbon atom, the other has connection to carbon as well. But if we look at the next atom, we see that we have one more connection to carbon atom, and here we have connections to hydrogen atoms only, so this has higher priority. And so on. So nothing special. As a general rule, just in case to remind you that alkenes follow some sort of stability order. Maybe it's not so interesting here, but if we are talking already about the substituents, please note that the higher substituted alkene is, the more stable it is. And here are energies of the hydrogenation. So how much energy you should spend to make something with that double bond. Okay. Here are some more examples. So these two alkenes are geometrical isomers or cis-trans isomers, and you may see that their physical and chemical properties are a bit different, as we would expect, because they have quite different 3D shape. So if we draw them in 3D, this double bond, it will not rotate, because pi bond it holds everything in place. And you saw that we need to spend some really large amount of energy to make this bond rotating. We are basically breaking this bond, rotating, and then recreating it back. If we don't do that, this bond stays, and we have different shapes of these molecules. And if you see that melting point for this molecule is 300 C, and for this molecule, so that's fumaric acid and maleic acid, is just 140, so 140 C. So they have quite different melting points. Similar type of stereoisomery can exist in cyclic compounds. So here are two cyclic compounds, and you see that we have cis-trans isomery. And once again we have, well, in this case just a little bit different melting points, but basically if we consider some chemical reactions and so on, we may spot some more difference. Okay, so one more reminder that if molecules are not mirror images of one another, they are called diastereoisomers. Okay, one more interesting thing, enantiomers. These are the molecules that are mirror images of each other. So here is an example, a few different molecules, and this example should basically underline why do we care about the chiral center and why does it make so much difference. So let me start with this molecule. It has just one substituent. I'll take this molecule and I make a mirror image of the molecule. Are they different?
No, that's the same molecule.
Yes, absolutely correct. It's the same molecule, so there's no difference. Let's take molecule with two substituents. Here is substituent Y, showed by this blue ball, and I make mirror image, and once again, are they different? If I take this image, this molecule, and I rotate it around this bond, can I make it to this?
Yeah.
Yes, of course. So this is the same molecule. They are just differently positioned in space. So it's absolutely the same molecule. And now we get to 4 different substituents. Let's check here. So I have well, two bonds to 4 different, let's say, groups. And here once again I have mirror image. But can I make from this mirror image the original molecule?
No.
No, I cannot. If I try to rotate around this bond, I can make, let's say, this blue ball and this blue ball to coincide, but I will have yellow ball instead of the green ball and green ball instead of the yellow ball. So rotating and translating that in space will not give me the same molecule. So this carbon atom is sort of stereo center of the molecule. And yes, you will have a problem of finding some these sort of carbon atoms in different molecules. Here are even few examples for you to show that sort of carbon atoms. So this one has 4 different substituents, and you see that hydrogen, OH, CH3, and so on. This one does not, because it has because that's equivalent of this one, so it doesn't. This one has double bond, so it doesn't even have 4 things to connect with, so no chances. So you might check these molecules and you will probably see how to spot that sort of stereocenters. Okay, what does it change? Basically, in sense of chemistry, if you do that, like, I don't know, like organic chemistry in a flask, it changes almost nothing. So almost nothing will be changed. In nature, we have certain chiral molecules, like proteins and so on, and if they are doing their job on something, they may distinguish between different chiralities. So that may be a big difference in this case. And from the physical point of view, there is an interesting effect that polarized light will be rotated by such sort of chemicals. Some will rotate it, let's say, more, some less, but anyway, they will probably rotate the plane of the polarization. So from the point of view of observer looking direct, so here is example, let's say, of a machine. If you are trying to consider this sort of rotation, so we have a polarizer that transforms light into the polarized light. Some questions? No. Here is the some sort
Sorry.
of yes, please.
No, it was accidentally.
Okay. Here we have a tube that contains our sample. So we have chemical in some sort of solution. And here you have another polarizer. If you remember the lecture number 1, rotating another polarizer, I can see when it gets darker, when light gets darker, when light gets brighter, and I can find out what is the angle of where is the plane of the polarization. So if we have some optically active molecules, they rotate the polarized light, let's say to the left or counterclockwise. They are said to be lever rotary or minus, whereas others rotate polarized light to the right clockwise, and they are said to be dextrorotary or plus. It's just arbitrary designations, but probably it's worth knowing that they exist. So rotating the polarizer, we might get the information. Is it rotating light to the left, to the right, and what is the angle of rotation? So for example, morphine is lever rotary. Sucrose that we all eat is dextrorotary. So if you have some sort of polarizers and tube, you can play around with just ordinary sugar and see the rotation. Okay, here I have something for you, but I don't remember what. So that's something about sucrose. So I told you that sucrose rotates polarized light, and here you see some sort of experiment. I guess this is a tube with sucrose. There is a polarized light coming from behind. So there's a large polarizer, and that light that is coming from there is polarized. And here is a polarizer on the top. I guess you will see now how this polarizer will be rotated and what we basically expect when polarizer is rotated. So the brightness of light should change. Yeah? Because we rotate this polarizer, and since the light is polarized, some part of it will go through the polarizer or not go, depending on the angle. And here we have tube with the sucrose. That sucrose rotates a bit the plane of the polarization, so we will see that darkening and brightening of the background and whatever we have in this tube will be at different angles. So let's look at it. So you see what happens. So the background darkens, while the solution of sucrose gets lighter. On the other hand, solution of sucrose gets darker, but at the same time the background may get brighter. This means that the plane of polarization of light that is coming from the background and that is coming from the tube, they have different angle. They are in different planes. So one is, let's say, in this plane, the other one is in this plane. So when you rotate...
Excuse me, are you playing the video? I don't think I can see it.
You cannot see that? Please look.
No.
So look inside the tube and what happens around the tube.
Yeah, now I can see it. Thanks.
Yeah, so inside and somewhere outside. And here is an example. And here is an example of the experiment with a little bit of formulae, and I guess there is some problem for the homework to calculate something with these formulae. Quite simple, I guess, so you should be able to handle that in no time. So what do we have? Here is well, our apparatus. We have a sodium lamp, so we get just one wavelength of that we will use for analysis. Here we have our solution. This solution is somehow concentrated. We know the concentration in the grams per milliliter. So please pay attention to this number. So what are the units? Are there meters, decimeters, kilometers, grams per liter, per milliliter, and so on? So yes, be careful with units. So we know the cell length. So the longer the cell, the larger will be the angle of rotation. So we will need to take that into account. And we have some sort of detector that detects that angle of rotation. And here is the formula. So we have some observed rotation angle in degrees. This is alpha. Oops. So rotation angle in degrees. We divide that by the length of the tube and by the concentration. Length of the tube is measured in decimeters and concentrations in grams per milliliter. Well, it looks a little bit strange maybe, but this is the standard choice that people do in in terms of units that we use, so there's nothing I can do. So if you will look up some tables and so on, well, how do you think? Why do we calculate this number at all? So such a tricky question for you. So why do we do all this? I have measured angle alpha with my device. So what else do I need? Why do I need to calculate something from that? Nope, no idea. Suppose we have the same chemical, but you measure on your device with, I don't know, cell length 1 decimeter, and I measure with cell length 2 decimeters. Do we get the same result?
No.
No, not at all. And that sounds not very interesting, because we have the same chemical, probably the same concentration, so everything is the same, but we have different results. So it's not good. If we want somehow to compare what we have measured, we should think of some parameter or some value that will be independent on the arbitrary chosen parameters of the experiment. You may choose a longer sample tube or shorter and so on, but you don't want that length to be included into the result, because we are interested in the chemical that we are working with. So we don't want to include there some arbitrary things that are not relevant to the problem. So if we know that the angle depends linearly on the length, it's a really wise thing to divide by the length and obtain some new parameter that is now independent on the length of the tube. And now if you measure with 1 decimeter tube and I measure with 2 decimeter tube, but we compare not the absolute angle of rotation, but this new parameter that contains division by the length, we should have the same numbers. And same thing goes with the concentration. So we may work with different concentrations of the same chemical. And we want to compare some parameter that has to do with the chemical itself, not with the arbitrary choices that we have made in our experiments, like length of the tube or like the concentration that we use for measuring. So that's the main idea. So by calculating this alpha D20, D means wavelengths of the that we use, and 20 means the temperature, because there may be some dependence on temperature and on the wavelengths, so we are just fixing them. But we are trying to exclude at least some parameters that are irrelevant, and just to leave something that has to do with the chemical itself. So in different sources you will find tables of this alpha, and they will describe you a chemical, and you can then recalculate what should you see if you take tube of certain length, if you take certain concentration, and so on. Or if you measure something, you can divide that and compare to the table. Do you really have that chemical that you think, is it pure enough or not? So this can be used basically as a guide to the enantiomeric purity of a sample. If there is another enantiomer in that tube, you might get pretty different result. So why do we have this rotation? Just a quick view. So basically every molecule twists light. So light is photons. Photons interact with charges. Molecules have a lot of charges, so nothing strange here. So if we if we have some light, it is somehow polarized, it meets the molecule, the plane of polarization twists. That's okay. The problem is when we have many molecules. Oh, I see. Okay. Someone asks a break. Okay, if everyone wants a break, let's take a break for 5 minutes.